So the next step on dealing with exponential functions is dealing with what's called a growth curve and a decay curve. As you saw from your example, we had a curve that went like this. And we had a curve that went like this. This is what's called a growth curve. And what happens is in f of x, when a to the power of x, a is greater than 1. Now over here on a decay curve, the values are decreasing over time, or as x grows. And what happens is a is going to be less than 1, but greater than 0. Where do we have examples of this? Well, they're talking about favorable conditions, populations of animals and bacteria will grow exponentially. More importantly, put it in a frame of reference for many of us. When a video goes viral on YouTube, so-and-so watches it, they tell two friends, they tell two friends, they tell two friends, it starts to grow exponentially. Or, on the other side of it, you have substances, radioactive being some of them, or asbestos, or different things like that, that decay exponentially. So over time, they decrease in value, but they decrease so they get cut in half and half and half, which is exponential decay. So, growth curves. Got a quick little example for us. Under favorable conditions, population of rabbits will grow exponentially. Suppose the population is given by p equals 100 times 2 to the power t, where t is the time in months. We can use this to answer the question, for example, to find the population after 6.5 months. Well, easy enough. I'll plug it on the calculator. I got it right here. We have, I'm going to look at the question out of the book because I can't see it while I have the calculator. We have 100 times 2 to the power 6.5 months. Enter. What did I do? I just put the graph in there. We didn't need to do it that way. I'm having a messed up day. I just wanted to go second function quick and go 100 times 2 to the power 6.5. Did I get the right answer? 90,051 rabbits. Same answer as the book. Now, that's as easy as using the calculator. Clearly, the population cannot continue to grow that way. We will represent it using the function that's shown here, but eventually over time it will flatten out. But that curve will be like this, like that. Now, let's do an example of a growth situation. During a locust plague, the area of land eaten is given by A equals 8,000 times 2 to the power 0.5n. So A is hectares, where n is the number of weeks after the initial observation. So n is weeks, n weeks, A hectares, or area. So find the size of the area initially eaten. Initially. So that means at the start of the experiment, so n is equal to 0. So we sub that into the equation. So part A, we sub in n equals 0, so I have A equals 8,000 times 2 to the power 0.5 times 0. Well, that means 0.5 times 0 is 0. So 2 to the power 0 is just 1. So our initial area is going to be 8,000 hectares. Nice? Useful? Find the size of the area eaten after 4 weeks and after 7 weeks. So, again, weeks is n. So B, 4 weeks. My area is going to be 8,000. 0.5 to the power 4. I look at this and I see 8,000, 1/2 power 4, which is 8,000 times 1/16, which is 8,000 divided by 16. Much easier to work with. And that gives me doing something really messed up. Holy cow, I'm having a rough go. Sorry about this, folks. I forgot about the 0.5 is not my exponent. Totally messing up the equation. My equation is 2 to the power 0.5 times 2. 0.5 times 4 times 2 squared times 4 equals 32,000 hectares. That looks a little better. Now, 7 weeks, A equals 8,000 times 2, 0.5 times 7, which is 8,000 times 2 to the 3.5. You plug that in the calculator and get 90,500 hectares. So, what are we going to do next? We've got part C. Use A and B to draw a sketch graph of A against N. So, look at that. Got a graph to work with already. Get rid of that dot. And we'll use our favorite points for doing this. There. These are going to be a little big, but our first point, our starting point, is at 8,000. I think that's going to be a little too big. So we're going to go back to just using the pen. 8,000, starting point. So this is A, and so this is hectares. This is weeks. Very important to label your graph so you know where your points go. After 4 weeks, we have 32,000 hectares. 10, 20, 30, 2. And then after 7 weeks, we have 90,050. So we're just above there. This is where it gets hard to connect the dots on these, but our curve should be a growth curve like that. Hopefully your line will be a little smoother, but that is what happens with a growth curve.